Yesterday I saw a viral question that had done the rounds on the social media, which showed this. It showed a Newton meter attached on one side to a string around some sort of jockey wheel with 10 newtons of weight pulling on one side, and a string on the other side of the Newton meter hanging over the jockey wheel with 10 newtons of weight on the other side. And the question was, what does the Newton meter say? Does it say A, 0 newtons, B, 5 newtons, C, 10 newtons, or D, 20 newtons? I'm just going to give you a few seconds to make a decision, and why not write in the comments what you think the answer is before I go through what it is and why. That's probably enough time. Okay, so you're looking at this, and there are some possible reasons why you might say what you might say. You might say, well, the Newton meter is in equilibrium because it's not accelerating left or right. Therefore, the resultant force on the Newton meter is 0. The answer is A. You might say, well, if there's two forces acting on it, each of 10 newtons, then the average force would be 10 plus 10 divided by 2. That's 10 newtons. Or you might say, well, there's 10 newtons one way, 10 newtons the other way, so you're going to get half that force, 5 newtons. Or you might say, well, there's 10 newtons pulling on it this way. If I held this point in place, that would be 10 newtons. If I held that point in place, it would be 10 newtons. And so we get both those forces acting, both of them stretching it, so it would be twice that amount, 20 newtons, or so on and so on. Well, the correct answer is C, and let's have a look at why that is. So I've set up here a Newton meter with a string on the bottom and 10 newtons. So that's 1 kilogram is approximately 10 newtons pulling down on the bottom of it. And let's just go and have a look at this. We can see that it does say on this scale 10 newtons. If I remove all of the weight from the bottom, you can see that it shows 0 newtons. There's no zero error or anything like that. Oh, moving out of focus. There's no zero error or anything like that. 0 newtons. And then when I put the weight on the bottom, which I've just taken off, it shows 10 newtons. So this bottom part, which is currently spinning, is experiencing two forces. It's in equilibrium, so we know Newton's first law applies. It has a downward force. The weight, gravitational force, is pulling this down with 10 newtons. But it's also being pulled up. And I know it's being pulled up by this string with 10 newtons because it's in equilibrium. That's Newton's first law. It's in equilibrium, which means the resultant force is 0, so it's not accelerating, and I can clearly see that it is not accelerating. So there's 10 newtons up. Now let's look at this bit of string. And I'm going to break it into chunks. So this white bit of string there must be being pulled down by this hook, by this weight here, with a force of 10 newtons. Now, why is that? Because of Newton's third law. I've already established that this weight, this 10 newton here, this object, must be being pulled down with 10 newtons by the force of gravity and being pulled up by 10 newtons to be in equilibrium because of Newton's first law. But at this point here, I can look at Newton's third law. The hook is being pulled up by the string with 10 newtons. That's what's providing the 10 newtons up on the mass. But the string must be being pulled down with 10 newtons by the hook. Hook's being pulled up with 10 newtons, string's being pulled down with 10 newtons. That's Newton's third law applied to the string and the hook. Now let's look at this part here, and hopefully you can see these colours and I can convince it to stay in focus long enough. This red part of string is being pulled down by this white part of the string, and the white part of the string is being pulled up by the red part of the string. And I've just rather arbitrarily coloured parts of the string to separate it out. Well, what's going on? Well, the white part of the string is in equilibrium. The white part of the string is not accelerating up or down. We've already established that the white part of the string is being pulled down with 10 newtons because of the hook. So it must also be being pulled up with 10 newtons to stay in equilibrium. That's Newton's first law. Newton's third law tells us that if the white part of the string is being pulled up by the red part of the string, which it must be because they're the only bits in contact, if the white part of the string is being pulled up with 10 newtons by the red part of the string, then the red part of the string is being pulled down with 10 newtons by the white part of the string. Now, the red part of the string is in equilibrium, so that means the red part of the string has a resultant force of 0. We've just established it's being pulled down with 10 newtons by the white part of the string. So the green part of the string, I don't know if these colours are coming through very clearly, the green part of the string must be pulling the red part up with 10 newtons. The red part is in equilibrium, so if it's being pulled down with 10 newtons by the white part, it must be being pulled up with 10 newtons by the green part, so that it remains in equilibrium. That's Newton's first law. But Newton's third law tells us that if the red is being pulled up by the green, then the green is being pulled down by the red. So now let's look at the green. The green is being pulled down by the red, but it's in equilibrium. Newton's first law, so it must be being pulled up with 10 newtons by the blue. Now let's look at Newton's third law. If the green is being pulled up with 10 newtons from the blue, then the blue is being pulled down with 10 newtons from the green. And we could keep going all the way up the string, and we can make these elements as small as we like. It doesn't matter. Every part of this string is being pulled down with 10 newtons and up with 10 newtons. It's in equilibrium, Newton's first law. So now we look at how the string connects to the Newton meter. Well, the string must be being pulled up with 10 newtons by the Newton meter, and that's what the Newton meter shows us. We can measure 10 newtons because it causes the spring to stretch. Fine, okay. So that means that this Newton meter is experiencing 10 newtons of force down. And if that was the end of the story, then the Newton meter would be accelerating downwards, but it's not. It's in equilibrium, so the resultant force must be 0, which means the clamp is pulling on the Newton meter up with 10 newtons. The Newton meter is experiencing 10 newtons of force up from the clamp and 10 newtons of force down from the string. So it's in equilibrium. That's Newton's first law. Okay, so that means that this clamp right now is being pulled with 10 newtons this way up and with 10 newtons this way down. That is what is happening. And it's calibrated to show us that that is 10 newtons of what we call tension in that string, 10 newtons of force. But the question wasn't about a Newton meter fixed at one end and pulled from the other, being pulled from both ends. Actually, it doesn't matter, because this is providing 10 newtons on one side of the Newton meter in one direction, and this is providing 10 newtons on the other side of the Newton meter in the other direction, exactly the same. Here is the experiment set up, with 10 newtons here, a string, a jockey wheel, Newton meter, string, jockey wheel, 10 newtons. What do we see? You might not be able to see it very clearly. It's on 10 newtons. Hopefully you can see that. You can see both scales there, which is a bit confusing, but let's just turn that round a bit. That might make it easier to see. That is 10 newtons. There's no tricks. You can count them. On this side, there is there are 10 100-gram masses. Yeah, these are 100-gram masses. See that? It says that there. There's no tricks. If I let go, that's now not going to be in equilibrium, so it's going to accelerate. And now I've got to do this one-handed because I'm holding the camera. I didn't think that through. And I could look on the other side, but we know it's in equilibrium. You can count them. That's also 10 newtons. And so this is in equilibrium, being pulled with 10 newtons this way, 10 newtons that way, showing 10 newtons. I know what you're thinking, but is it actually, or have you just incorrectly calibrated it? Well, let's take off each of these then. Let's just try and do it like this, without them falling, one-handed. I'm going to have to walk my hand along the string to get to here. Right, now, the only change I've made is I've now moved that one, but this one is still hanging over the edge. That's not bad going for one-handed. And I'm now holding it in place, and it still shows Hopefully that's in focus. You can see it still shows 10 newtons. There's been no change. It still shows 10 newtons. And then I can remove the other side. Well, actually, I can just let that fall to the floor to relax it. And then let's have a look. And it shows, get in focus, get in focus, get in focus. It shows 0 newtons. It would do if the darn thing got in focus. There we go. So there's no tricks. That is 0 newtons. It does support that one and become 10 newtons. And support that one is still 10 newtons. Now this is, of course, ignoring friction in the pulleys. That would change things somewhat. But there's no myth to this. Why is this confusing to people? Because they don't understand Newton's first law and Newton's third law. But look, the resultant force there is 0 right now. If I hold that, I'm doing nothing. It doesn't make a difference. I can pull it this way and then relax. No difference. In fact, I could push this to here and then stop it and it would stay exactly where it's put. Why? Because it's in equilibrium. Better than that, if these were frictionless pulleys, if I pushed it and let go, it would keep on moving. If these were frictionless, it would keep on moving and not stop because the resultant force is 0. Newton's first law means its velocity would not change. Actually, you can see just how bad the friction is on these pulleys by how much it slows down and stops. And not great pulleys. And yet, even though these pulleys have friction, it still shows pretty much exactly 10 newtons. So there we go. Hopefully that solves that conundrum.